Hello, everyone. Welcome to our statistics course. Statistical study itself, it consists of three things. Okay, one is to prepare, analyze, and conclude. Okay. To prepare means to prepare the data, analyze the data, then conclude what the data revealed. Okay. So, statistical thinking is slightly different in the sense it is very much mathematically based, but it involves critical thinking and the ability to make sense of the results. Okay, so it also requires us to have the ability to execute complicated calculations. So we generally understand data, what it means and so on. But statistically, it's important that we understand the definition. So let's go ahead and define some of these important terminology in statistics. So data indicates that, collections of observations, basically. So it's obviously what you're interested in, right, to observe. And the information you collect based on that, that becomes your data. So we have plenty of collections, right? And so even within a collection, we may be focused on a particular few details there. So for instance, let's take a student's record. So there will be the student ID, gender, age, background, ethnic background, the number of courses completed, where they completed, the GPA scores, the grade scores, so on, right? You can have plenty of these details. So within that, what could be your interest? And that will become your data because you are drawing the information you need. So that could come from an existing, from an already collected data, or it could be something that you are interested in. You want to observe. For instance, you want to see how many red cars there are in the city. And so you could go ahead after that data. And if you collect that information, either through a survey or through collecting publicly available data, or if you wanted to take that information and focus only on a particular street, you could say how many red cars passed the street in a particular month. So, you could decide what your data could be, for what length of time you want to observe the data, and so on. So it means a lot. It could mean many things. So we always have to define what we want our data to focus on. Then we talk about statistics, this very course. This is only introductory statistics, and we have all the way up to a PhD that you can earn in statistics. So it's a science, it's a study. So what does it do? What do we do there? So it is the science of planning studies. Okay, you need to plan first so that you know your focus. And if it's an experiment, you need to plan and set up the experiment so that it is valuable, viable, valid, and so on. Obtaining data, organizing it, summarizing it, then presenting that data. And I say presenting, you just have your notes or your data with a bunch of raw details in it. So you can just present it like that. So we like to tabulate it, organize it in a table or a graph or a chart. So presenting is important. Analyzing would involve more complex calculations using statistical procedures, statistical techniques that are highly mathematical in nature. And then interpreting those data based on what you analyzed, it usually helps you to make that decision. That's the beauty of statistics. It gives you step-by-step process on how to make your conclusions and so on. And interpret your data, and then it teaches you also how to draw conclusions based on them, because sometimes you have data that needs to be verified for some biases. Sometimes it has to be verified for some factors that may be affecting it, which may be lurking in the background, and so on. So it's a beautiful subject. It's a beautiful science. And today the biggest deal is all the data we have that's available. So having a good understanding, a grasp of this field is very beneficial. When we have data, we want to, as I mentioned before, want to have a focus on what it is what we are trying to study. So the population, by definition, is the complete collection of all measurements or data that are being considered, right? So all of it that you're considering. If I say, I'm looking at all the red cars, is that my population? Then it means all the red cars in the world. If I say all the red cars in the United States, that becomes the population where we're talking about all the red cars in United States. If we're talking about all the red cars in California, then that becomes a population. So you can reduce it to whatever you want. But when we say population, we mean all of them in that group that you're considering. So if I say California, then I'm talking about all the cars in California. I'm not leaving out some of them, right? So you want to really define what your population is. Usually, usually our interest is to make inferences about that population. So that is the reason why you need to be clear about what population you're focusing on. Based on your study, are you trying to conclude something or make inferences about something for the entire United States, or is it for just a state, or is it for a county, is it for a street, is it for a particular group of people? So we really need to know what we are trying to make inferences about. So knowing what your population is absolutely important, understanding that it is the complete collection of all the measurements from that information that we're considering. So we saw the population. Now let's take an example of a population. Could be census, right? The census is where we collect data from every member of a population. So that's why it's a huge undertaking, because you're going after every person. Well, the focus is every person. We don't know if we got every person. There's probably some ways to account for it, but it's nearly impossible to get information from everybody, right? And meaning in the population. So every member in the population is going to be very challenging, provided your population is sizable, right? And so we always like to understand more about the population using a sample. And a sample, by definition, is a sub-collection of members selected from a population. So it's a sub-collection, a smaller group that is drawn out of the population. This way, you can have more control over the group, meaning you can collect all the details you want from every member of the group, of that sample, because you cannot do that for the population. You're trying to do that from a sub-collection of that population. So let's read this example. In the journal article, Residential Carbon Monoxide Detector Failure Rates in the United States, it was stated that there are 38 million carbon monoxide detectors installed in the United States. When 30 of them were randomly selected and tested, it was found that 12 of them failed to provide an alarm in hazardous carbon monoxide conditions. Okay? So try to understand the background. This is from a journal article. Okay, so there are 38 million carbon monoxide detectors in the United States installed. When 30 of them were randomly tested, 12 of them failed. So my question is, what do you think is the population in this article? Okay, if you figured 38 million on this one, that's wonderful, because we got all of them. That's all of the ones installed in the United States. It might seem, we just said that it's difficult to get all the information from the population, but based on the accounting, again, we assume that all of them did their record keeping really well. And so this is something that can be obtained pretty much close to what the real value, the real information is. That is that there are 38 million carbon monoxide detectors in the United States. And what do you think is the sample? So let me write there beside it somewhere. That is the population. Right? And what do you think is the sample? Well, you're thinking, is this 30 and there's 12. Which one could be the sample? Remember again the definition. The definition is that a sample is a sub-collection of the population. So then if there were 38 million, you can't go after all of them. So then we will choose randomly some of them from that population, and that was 30. 30 of them were randomly selected and tested, right? So the randomly selected ones, that becomes our sample. Okay, the 12 that didn't work, that is extra information as far as the population, the sample are concerned. That information can be used to draw some conclusions and so on. But remember, the objective here is to use this sample data, 30 carbon monoxide detectors, as a basis to draw conclusion about the population for all carbon monoxide detectors. Okay. And to draw that conclusion, to make it meaningful and helpful, we of course employ statistical methods. If you recall, we originally said these are the three things we do in statistics to prepare our data, the context and everything, analyze and conclude. So just to run the gist of it, under the preparation phase, we look at the context. So what do the data represent? What is the goal of the study and so on? And then we go to the source of the data. We try to see how to obtain our source. If we are getting this information firsthand, if we are the first ones to draw this information, we have to make sure that it is all sound practices. We're not biased when we obtain the data. If it's coming from somewhere else, we want to, from us or somewhere else, we need to make sure that the data comes from a source that is free of, other biases like special interest groups, so that there is no pressure to obtain results that were favorable to the source. Okay, so today we can see, from history that there are some studies that are funded by the very groups, that we want to see as causing the effects, the ill effects of their product. For instance, the cigarette companies, before they could acknowledge and admit that cigarette smoking causes cancer, before that could be established, the cigarette companies themselves funded the studies. So, the researchers were kind of pressurized to provide data that was favorable to their funders. So for a long time, there was resistance to that information. Today, we all know that, but there was a time when this was shrugged off. Many doctors were roped in to say it was totally fine to smoke and that it did not cause any ill effects, let alone cancer. We now, in recent years, we've seen the same thing to do with sugar. So we have plenty of these companies, we have these soft drink companies, carbonated drink companies, these big mega giant companies. They are funding a lot of studies, and many of those results came back to say that it was nothing to do with the sugar content was not really bad, and that it was about the caloric intake of that person, and that was the reason why there was obesity, cardiovascular diseases, hypertension, and every other comorbidity that one would have. It was all because of their caloric intake and not necessarily because of the sugar content. Today, we know that that is entirely false. And sugar itself is so refined, and we know that that's absolutely, it's just poison, because we're eating more than a year's worth, I think, in a few days if you constantly consume these drinks. And our body is really, really, really fighting hard to eliminate the toxins in our body, but it's overworked when we kind of stuff it with all the sugar. So it's not just the drinks alone, all kind of processed foods. There's not one food where there is no sugar. It's directly or indirectly brought in. And so that is something we have to really pay attention to when we do the preparation of our data. What does the source, where does the source come from? Is it biased? Is it coming from a special interest group? Now, sampling method, that is very important as to how we obtain this sample. It has to be randomly selected, and the randomness is what keeps it unbiased to a great extent. So we want to use procedures that tout the random sampling design. So there are various ways we can do it. We're going to look at that shortly, but we don't want to do things that are blatantly biased, where you just go and choose group of people who volunteer to do it because only those who are interested are going to volunteer, right? And so we want to make sure that we are avoiding all this biasness there. Then analyzing, that is where the yellow portion is where it becomes more mathematical, because now you've got the data. You're going to use statistical techniques to kind of cleanse the data to see if there are any outliers. And we're going to talk about all these, but we just want to see how the data is distributed, how it can be tabulated. Are there any missing data? And did anybody who were selected in that random selection, did the subjects refuse to participate? If that happened, then did it reduce the number of participants to a point where the number of, the data, the number of the sample size basically, was it really too small and so on? And then, of course, there are a lot of statistical techniques and methodology. Technology can help you with that. Now, ultimately, it is important to know how to conclude, because some analysis can produce results that are statistically significant, but may not be practically significant. Some may be practically significant and may not show up as statistically significant. So we really have to see the difference to see what significance they carry. So it's very important the way we conclude it. And for that, again, there are various statistical techniques to help us measure that. So when we talk about voluntary response sample, right, we see that this is a case where respondents themselves decide whether to be included or not. Okay, it's a self-selected sample. So by the nature of this setup, it's seriously flawed, because we really cannot make any strong, meaningful conclusions about the population, because it started off with a strong possibility of a bias. Right? Those who are really interested and vested in that particular question from that response sample, they are the ones who are going to participate in it. And so we're going to have that strong bias there because we're going to get one way or the other only those who are interested in registering their comment, whether it be positive or negative for that question. So again, it is a very specific group, and it all depends on how it's presented too. But, for example, we could think of internet polls. Okay? With internet polls, it may be open to all, but only those who are interested are participating in it. So we don't really randomly select people. Mail-in polls, there again, right? Mail-in polls, recently now with the coronavirus situation, and with the question of elections and how to cast the votes, in-person votes is usually the reliable way, because we can cross-verify and so on. But if it's a mail-in version, then there is room for errors in the sense that bias, because people who no longer live in that address or people who no longer belong, who are deceased, who are no longer in the country, or for whatever reasons, those could be misused. There's the ability to have that abuse take place in a mail-in option, because we have no way to verify, because somebody's going to write that information. If they have bad intentions, they will misuse it. On the other hand, if it's in person, then there is some kind of verification, because we have that system and the person has showed up in person. Anyway, so we can see that in these kind of mail-in versions too, people can decide whether to participate or not, and there is room for abuse. Telephone call-in polls, like newspapers, radio, TV announcements, right? They usually call out and say, would you like to participate in this show or in this poll? If so, volunteer. You can voluntarily call this special number and register your opinion. So these are telephone call-in polls. So anything that is prompting the respondents to decide whether they should be included or not comes under voluntary response. Okay, so we can kind of see how this can be true in a particular scenario. Take a look at this example. Nightline asked viewers to call with their opinion about whether the UN headquarters should remain in the United States. So Nightline is a news show. Viewers then decided themselves whether to call with their opinions, And 67% of 186,000 respondents said that the UN should be moved out of the United States. In a separate independent survey, 500 respondents were randomly selected and surveyed, and 38% of this group wanted the UN to move out of the United States. So let's compare these two surveys. Okay, Nightline asked the viewers to call in with their opinion. Okay, so obviously the viewers who called in decided to be part of it, chose to call in. And there we see 67% of 186,000 respondents said it should be moved out. On the other hand, in a separate independent survey, 500 respondents were randomly selected, and 38% of them said we wanted to move out. So 67%, which is a huge majority, 38% is a minority of people who wanted it to move out. So let's see what's happening. Which one should be considered? Now, if you look at the Nightline survey, it's 186,000, so it is a huge number, and we really want our sample to be really large because that is a better representation of the population, so we really love that. And out of that huge number, 67% said this way. So we tend to think, well, the other one, the independent survey, had only 500 respondents. It's so small compared to this. But the stark difference is that the two polls produced dramatically different results. For that reason, even though we had 186,000 respondents, remember that Nightline poll was all voluntary. So these were volunteers, whereas the independent survey were randomly selected. So even though 500 seems to be a smaller number, it is still a sizable number. It's statistically a good number. And so it's definitely smaller, but then these are randomly selected. Therefore, this is far more superior sampling method. The independent method is far more superior than the Nightline. Again, remember, Nightline poll it's failing at many levels because, first of all, these are volunteers, so it's a volunteers and self-selection. Secondly, only those who watch Nightline would be part of it. So right there you have that bias. Only those who like that show will be watching it. Thirdly, only those who watched that particular show that day, or those times when it was advertised this way, would be participating. So you can see that it's a complete bias, and therefore the results also tend to show that bias, right? So we want to really understand that. Now, when we analyze and explore these the data is collected like this, we want to make sure that we use appropriate graphs. Because it's a visual thing, and statistics is really nice in the sense that it tries to explain these things to lay people, not to people who already know statistics. So to explain it to a lay person, meaning when I say lay person, a non-statistical or non-mathematical background person, we want to be able to show them these things visually. For that, graphs really, really help. And using the appropriate graph makes meaningful conclusions because, again, we can distort the data by using the wrong graphs or misrepresentative graphs. Now, when we use statistical methods, again, remember, you don't really have to be extraordinarily great in your computational skills, although that will be helpful. Today, we use software to compute these one-scores, so it's really not the question of computation skills. It's what a good statistical analysis needs is a lot of common sense and careful attention to sound statistical methods. So we should know what these methods stand for. Therefore, we'll be able to provide that information soundly. So what about misleading data? So we could have, mislead. These are potential pitfalls. Okay, when you have these kind of misleading data, could be pitfalls because whatever you do thereafter, if you did analyze it well at the beginning, you can have, if you had a bad data to begin with, no amount of statistical torturing can salvage it. So then we have misleading conclusions. That is to be avoided. So when you form a conclusion based on an analysis, we should make those statements clear using, not too much of statistical jargon, so that information is clearly and correctly understood as intended, and not meant to confuse people who are receiving this data. And then when we talk about sample data, so it's better to measure than report. What do I mean by that? Now, when we have, say, we use the right sampling technique, which was unbiased and random selection, and we collect the data from people, okay, who were selected. Now, when it's better for the researcher to go take the measurements, whatever they want. If they want to ask about their GPA, or if they want to ask about their preferences, things like that, whatever information they want, if they can go themselves and collect the data, measure it themselves instead of asking the subjects to report those results, that will be really important, because that shows responsibility on the researcher's side, and it ensures that the participant gives their data, and it's not reported, where again there could be a misunderstanding of the question itself, or there could be an abuse of information where somebody else submitted that information on the subject's behalf, and so there will be bias or distorted information, or simply malpractice. So we want to avoid all that. We want to make sure that, because these are really important. If we don't arrest this in the beginning, we would end up having bad data. So you want to watch out for that. Loaded questions. This is interesting. Most of the data is collected these days through surveys. They ask these questions. And I do that too, in my courses, to see how well of a job I'm doing in my course, how the course is set up, how the students themselves are performing in the course. So I'd like to run surveys. They are very, very meaningful and highly effective. However, when we ask questions, sometimes we can have loaded questions, okay? And so if the survey results are not worded carefully, the results of a study can be misleading. Okay? Then we have order of questions. These seem very innocent, but sometimes, it can be unintentionally loaded. So if we ask a question, is air pollution caused by industries or by vehicles? The order in which you place them, industries or vehicles, it can move people to blame the industries. But if you put it the other way around, is air pollution mostly caused by vehicles or by rather than industries, then you tend to lean more towards the vehicles. So the order of questions, sometimes it's impossible, right? You have to put it in some order. So I understand that. What we're saying is we're acknowledging that sometimes these questions can unintentionally get loaded because of the order of the items being considered. Okay, that is why they usually use they put the order and they say these are in alphabetical order. It's not ranked in any way, so it's in alphabetical order. That way, it kind of clears the minds of the respondents, so that they are not going by what appears first or what appears last, but by the fact that it's alphabetically arranged, so there was no ranking inbuilt in it. Non-response is another pitfall, where when someone is unavailable or refuses to respond, that is a non-response. And that can mislead because you have missing data there, right? Percentages is another big area where, misleading data happens, because some studies cite percentages in a misleading manner, okay? Remember, 100% is all of it, right? So if they make any reference that exceeds that 100%, then their references are not justified. We have such requests even from our own math students sometimes. They say, shouldn't I get 105% because I participated in the extra credit opportunity? Then I have to tell them, you know what, you already earned 100% in this exam if you did really well. So they say you already earned 100%. So you got all of it. Extra credit is to add to a little bit to that particular assignment, to boost it slightly. You can't dramatically expect it to boost it in such a manner. But then they collect all the the extra credits, and then they say it has to be applied where it exceeds 100%. It's meaningless, right? Mathematically, it's a misleading percentage. So I understand some schools do that. I wonder why. But it's just not the right approach. It's mathematically misleading. So if you've earned 100%, you got all of it. So we should be happy. All right. So these are some of the pitfalls I wanted to discuss here. When we talk about types of data, this is super important here, that we define the numerical measurements, right? Ultimately, that is that's the way we collect data, because we're collecting this information. So if I say how many red cars there are, that's going to give me a number, right? Between 9 a.m. and 10 a.m., I can say there were 13 cars. Between 1 p.m. and 2 p.m., there were 7 cars. So you're going to come up with that number, right? So the number of cars, number of red cars could be a measurement of your population, right? It's a characteristic. So you're measuring it. Or you could take the, if your interest is in finding the, it's about the heights, if your data is related to the height of, 8th graders, then you could say, well, if it's the height, then you want to measure it, right? So that numerical measurement, this many inches, that becomes your data. So whatever describes some characteristic of your population, that numerical measurement is called a parameter. Okay, so in general, it's called parameter. So mean could be a parameter, average could be a parameter, number of cars could be a parameter, as long as you can numerically measure it. Think of this alliteration here, right? The P and the P. So that which describes numerically a population is called a parameter, okay? Some kind of measurement. And you can see that also happening with statistics. Statistics is the study of, it's a discipline, it's a field. Statistic indicates the numerical measurement that describes the characteristic of a sample, okay? S and S, P and P. So in future, when we talk about inferential statistics and so on, we'll be talking about test statistic a lot. We'll be talking a lot about it. We'll talk a lot about parameter, particularly in confidence intervals and so on. So parameter is a measurement, a numerical measurement that describes some feature or some characteristic, some quality of a population. Statistic is a numerical measurement. It's a number that describes some quality or characteristic of a sample. Okay. Your data can be of several types. In particular, there are 2 broad types. The first one is the quantitative data. As the name says, you see the word quantity in it, right? So quantitative is measurement of a quantity. You can measure a quantity by counting the number of things if it is discrete, or you'll have to measure it using a tape, in some way using a tool to measure it. So you can count them, or you could measure them. For instance, if you're talking about, let's say the number of $100 notes, bills, $100 bills. So you will get, a whole number, right? You can count and say, oh, I saw that there are 55 $100 bills. You can't say there are 55.3 $100 bills. You can't give it in a fractional setup, right? So that is what we mean by counting, where you're able to count, and that will be discrete. Whereas if I were to find the weight of a person, then that would be, 110.5 pounds, or it could be 200.7 pounds, and so on. So you give that measurement with the fractional component, because you can have that, right? So it doesn't have to be exact round numbers. So counting, think of it as using your fingers to count. You can't count fractional parts using your fingers, right? So that's one way to understand the counting idea, right? Whereas the measurements usually would go into the fractional part. So if you're measuring the length of a wooden block, you can measure it to be 3 and 7/8 inches, 3 and 7/8. So you can do all those fractional measurements when we do the measurement as a continuous measure. So the example for quantitative could be age, weight, right? It could be like, for example, the length of a call, a phone call, right? So the phone call could go for 2 hours, it could go for 2.5 hours, it could go for 2 hours and 17 minutes and 33 seconds, right? So we can have all those quantitative stuff coming under the quantitative data. Then there is another way we can obtain data. We call it the categorical or qualitative data. So categorical or qualitative data, as the name says, it's quality, right? So we're talking about measuring the quality of something. So it cannot be, numerical then, in the sense like as a representing a measurement. So this consists of names or labels, okay? So when I say names, we could, for example, we could talk about gender, right? So the gender would be male or female. So you have names that or labels that describe that gender option. Sometimes it could be shirt numbers of athletes. Now remember, I intentionally brought this example because it looks like numbers. We said there should be no numbers. But remember, these are shirt numbers. They do not mean anything. You can't multiply, add, or divide these numbers, right? It's meaningless. Because these numbers are substitute for names. So these are labels that are numerical looking, but these are not to be used for computation, right? We just use those numbers as an easy way to identify the corresponding athlete. So remember that we could have the color of the eye. That again is a quality. It's an attribute. So you could say green, blue, brown, hazelnut, all that. So you don't have a number to indicate that. So when we talk about qualitative is pretty much clear in the sense it's about quality, but quantitative, I was talking about how some numbers can be counted, some numbers can be measured. So that's the whole idea of understanding quantitative, that can be branched into two categories. One would be called the discrete, and the other one is continuous. Okay. Remember, in English, discrete has a different spelling, D-I-S-C-R-E-E-T. Discrete means quietly, without anybody knowing, in a very subtle manner. But here, discrete actually means that it is countable, it's finite, it's countable. As in, you can jump from one to the next number, so 1, 2, 3, 4, by looking only at the whole numbers. Okay? So it's like tossing a coin, the number of times you toss a coin, right? So it cannot be a fractional number of times. So it can only be whole number of times. So whole numbers. Think of counting with fingers. Or counting by pointing, right? So these are kind of examples for you to remember that we are counting them. So we are jumping by the discrete values. So 1, 2, 3, 4, 5, 6, and so on. On the other hand, when we say continuous could be finite or infinite too, right? But meaning, I can give a limit, but then the measurements within it will be, let me point to you here, okay? So 1, 2, 3, etc. To 100, let's see. Here, this would be generally infinite, okay, even though I have a finite limit where it starts and where it ends, okay? And it is not countable. You cannot count it. So think about how you cannot count it with your fingers. You need a tape You need a tool to measure. So that's how it is. So this 1 to 100 would be an interval 1 to 100. Remember the interval notation? So that means if I had, say, a number line, right, and it's a zoom in between 1 and 100. It is all these values between 1 and the 100. So then what is the number that comes right after 1? Please don't tell me it's 2, because you've done your algebra. The number right after 1, nobody knows. Because if it is discrete, yes, the number right after 1 could be 2, because you can only jump by whole numbers. But in a continuous setup, the number right after 1 could be, if you said, okay, it's 1.1, then I would say, what about 1.01? And you can counter and say 1.001. That'll go 1.00001. And you can have like a million zeros, a million zeros, and then a 1. It is still not anywhere closer to 1, because the number right after 1 could have any number of zeros to outdo a million zeros, right? Million is a smaller number compared to infinite possibilities there. So do you understand what I mean by measurement? You can only measure it. It's an interval. You really cannot single out the numbers and list them like you can list them when you count. You can't put a comma and list them. So it is an interval. It's a measurement. Because even if you, forget 100, even if you were to measure this between 1 and 1.5, you have infinite possibilities, right? If you're measuring between 1 and 1.1, there are infinite possibilities because you're looking at that interval. So I want you to pay attention to that and be really clear about what we mean by interval versus, a listing. So just to reiterate the point, I can have it from 1 to 1.1. You can have infinite possibilities right there because I'm zooming in closer and placing 1 and 1.1. In 1 to 100, it's like it's zoomed in, not too close, so you can see the 1 and the 100 in that scale. Here I'm zooming really close, so you can see between 1 and 1.1. So I want you to pay attention to the difference here between discrete and continuous. Okay, so these are lengths or distances, and these are counts. Okay, so counts, measurements, as in lengths. Okay, so think of measurement, measuring tape, measuring tool. Counting, think of it as a counter, finger counting instead. Let me talk about levels of measurement, and we have 4 such levels. So under levels of measurement, let's focus on the first level. It's called the nominal level, and here we have the data is characterized by, or data consists of, names, labels, categories. Okay, so it's qualitative in nature. The data cannot be arranged in some order, right? For instance, if we were talking about the eye color, you can't arrange it in some order. When I say order, I mean high to low, kind of priority. You can arrange it maybe in alphabetical order, but not in some kind of priority. Okay? So if you have yes, no, and undecided responses, how would you order them? Again, you can only do it alphabetically, but no one response is superior to the other, right? Yes, no, or undecided. So that is kind of the definition here, or the example here for nominal. Next, we have ordinal measure, ordinal level, let's say. And here, it involves data that can be arranged in some order. Okay. So data can be arranged in some order, but no meaning in determining, no meaning in differences, let me say. I'll explain it now. So here again, it'll look more like nominal data, okay? So, let me quickly go back and say, example for nominal data would be yes, no, undecided, right? So these are categories or names, but they cannot be arranged in any priority. For ordinal, let's think of this as course grades, okay? If you think of course grades, then you know that we have A, B, C, D, and F. So here there is some kind of ranking, right? Because A obviously is on the top, it's exceptional, and F is failing. So there is that order, but there's no meaning in taking A minus B or C minus D. We don't do that. And therefore, here too it is some kind of a description. It's a qualitative data because you have letters, not numbers. But these are, and they can be arranged in meaningful order, but differences are not meaningful. We can't take any differences. Let's move to interval level. And here, your data can be arranged in order. Differences are going to be meaningful, but we don't have a natural starting point. It's an interval, and wherein we don't have a natural starting point. There's no quantity that was present in the beginning. Let me explain that here. First, let me write this information here. Okay. So data can be arranged in order of priority. Differences can be found and they're meaningful. But there is no natural zero starting point. Okay. So what could be the example here? Well, we can think of years. Okay. So you can have in the year 1000, in the year 2000, in the year 1776. You can do all this, but we don't have the starting year. We might think, well, what about AD and BC? Okay, again, it's an interval. Time is endless, so we really don't know when it originally started. We don't know the first day, right? That ever was. So we don't know. We don't have a natural starting zero point. However, we have intervals. So when we say BC and AD, we are actually talking about intervals, right? So from AD, that's when kind of modern history can be measured. So from AD onwards, from AD 1 all the way up to what we're now in 2020. So we have AD measurement there. So we have, when we go to 21, 22, that just means that we have 2022 years, 2025 years, and so on. So we can measure over an interval, but we really don't know where it began. And the last, we said there are four levels. So the last level would be ratio level. This is the interval and the ratio are quantitative, whereas the other two were qualitative. So here you can clearly see that the data can be arranged in order. Differences can be found. So I'll just say differences are found and can be meaningful. And what's missing there is found here. There is a natural zero starting point. I'll give you a relatable example, okay? You can think about class times, okay? if I say the class times are 50 minutes, you know that there was a natural starting point, right? So it was from 2 p.m. to 2:50 p.m. So we know that natural starting point was 2 p.m. That class did not exist or operate or begin before that, right? So there is a natural starting point. If it is for 100 minutes, whatever, right? So if there's a natural starting point, what it allows is that we can have ratios, fractions, right? So you can compare them. So differences and ratios are meaningful. That's why it's called ratio level. You can do all these things. You can play with all these things in the ratio level. You couldn't do that if you didn't have a natural starting point, like in the interval level. Okay. So I just want to say that because we were talking about how to collect data, how to organize it, what kind of data there is, what types of data there could be, I want you to understand that this is the world of information, was it overload, right? So we do have plenty of information. There's plenty of data available thanks to all these smart devices and all the technology that we use today. So we have big data, which basically refers to data sets that are so large, so complex that these analysis cannot be used, cannot be done using traditional software tools. You really need these data to be run parallelly in multiple computers, you know, huge servers and things like that. So some companies do that. They thrive on this data and they use this data for various purposes, for government purposes, for reporting, the statistics, Department of Statistics. It could be for marketing purposes. It could be for production purposes, for financial purposes, economic purposes. You have all these things happening, right? So we have that. And there's, of course, data science. This is exploding now because, the application of statistics, computer science, software engineering, all of these things become relevant. Sociology now with all the medical improvements and research there. So it's exploding in every field that you can see. And so how do we use this data? How do we translate this data? How to interpret this and make it into something meaningful? Then we also have to pay attention to any missing data, because when you have all this data, you want to make sure that it is valid, right? When you begin to analyze it. So in terms of missing data, you could have data missing at random. What this would mean is that is the likelihood of that data missing is independent of its value or other values in the data set. Okay, so meaning this data that is missing is just as likely to be some other data that is in the data file. So there is no specific reason why this particular data was missing. So it's independent, right? In that sense, it could have been anything. So it's random. Any one particular file could have had that same impact of getting lost, like this one that was lost. That is missing at random. Okay, of course, there is missing not at random. What this would mean is if there is a reason that is connected to that information that is missing. Okay, so now for instance, we have, if there was a data entry error, right? Someone was entering the data and then, they missed this particular field or this particular data set altogether because they just skipped one row and went on. Now, there is a reason for that missing. The reason was human error. Okay? So we want to take care of that as well. So how do we correct them? To correct them, the most common method is if there is one field that is missing, okay, then you remove that entire data set. If there is a missing data, then we want to delete all subjects having any missing data. Okay, so that way we're keeping it random. Okay, something was missing, so we'll remove all those ones that had missing information. So everything is gone. The less popular and the less ethical way of correcting a missing data is to impute data. Impute meaning to substitute values for them. So we don't want to do that. We want to make sure that our data is collected appropriately. So how do we collect data? We want to make sure that there is no bias, right? Remember we spoke about that. So we want to make sure that we collect a sample using simple random sampling technique. Okay? Simple random sampling. So we'll come to that. Okay. Otherwise, if you didn't use this method, then we will not be able to utilize the data that we have obtained because it will be rendered utterly useless. Now, the word random is so important because obviously randomization means that there is no bias there. You're not picking and choosing. Nobody is volunteering. You're selecting them at a random, using a random process. So usually when we use the randomization, where you have one group that was, where there are two groups basically, they are identical as much as possible. They're identical in every respect except for the very thing that you're trying to test between them. This is what they do with medications, right? If they have two groups and the people who are selected are, equivalent in both the groups, they might have the same illness and all other backgrounds match. Whereas the only thing that's different in each group is that one group receives the actual treatment, the actual medication, while the other group receives a placebo, which is a sugar pill, basically. It has no medicinal effect, but it is to, again, treat the two groups equally so that they perceive that they're receiving the medication. Because if you don't give them the medication, they know that they don't have the medication, and that can have some emotional impact or psychological impact in the study. So to keep it equivalent, we have these two groups, and it's randomized. Who gets into which group is randomized. So people don't get to select and say, oh, I'll be in the placebo group or I'll be in the treatment group. They can't say that. If that you lose the whole value of the experiment. But you send them randomly. You select them randomly, and they are assigned to these groups in a random basis. And that is known as the gold standard for research, for experiments, because it is so effective and it eliminates anything else that could be causing that impact, and it only focuses on the very variable you're trying to study. The variable is that, is this medication effective or not? And so it really helps us with that. So there are two types of data that you can collect, right? One is observational. We saw how we can observe something and get it, from by ourselves. We can observe it and obtain that information firsthand. Or you could also get that information through an experiment, like I just mentioned about the medical scenario. So it can be an observational study or a medical study. The difference is that when you observe, you do not know, what do I say? There is no effect on the subject, okay? So no modification, let me say. So you look at the scenario, the context, and take it as it is. But when you experiment, of course, you modify or treat, right? That's the treatment. You modify or you apply a treatment to the subjects and then observe the effects of your intervention, of your treatment. All right. So there was this interesting study where to highlight the difference or the meaning behind observation experimentation is that, someone observed the data, past data, and to conclude that ice cream causes drownings. They used some past data and came to this conclusion. Ice cream causes drownings. Because the data showed increase in ice cream sales are associated with increases in drownings. When you look at that, it sounds absurd. How can these two be related? Yeah. So what happens is if you simply observe, without looking at it, looking at the context, you just observe from some past data, the researcher is prone to make the mistake of missing the lurking variable, which was the temperature. What was common to both these, what was happening, what made these associations was that the lurking variable, or the background variable, you can't see it, you didn't see it because you didn't study it, But that was what's causing this association, where the temperature was the miscreant. You know, increase in temperature drove ice cream sales, and it drove people to the beaches to swim, or at least to the pools, maybe. And so, when because of the temperature, it seemed as if the more people, the more ice creams were sold, there were more drownings, somehow relating those two. But those two were impacted by temperature. So, to even understand this impact, one shouldn't simply observe in this case, one should experiment. Because when you conduct an experiment where you create two groups, one group gets ice cream, the other group does not get the ice cream, and then you want to see, if the drownings increased in this group, or was it the same? So then if you see the rate of drowning victims, you can see that ice cream consumption had no effect on drownings. Therefore, this is a case where we're trying to say, well, experiment is clearly better than observational study. Replication can be another way to design your experiments, where you repeat an experiment on more than one individual. So you're able to replicate or repeat. Okay. Blinding is another technique, right? In experiments where the subject doesn't know whether he or she is receiving a treatment or a placebo, right? Like in those the two groups. So they don't really know, because they receive the pill that looks alike. So one is really the actual pill, the other one is a sugar pill, but they don't know because it's a blinding technique. Okay. This is very important because, sometimes people just seem to report improvement. It's known as a placebo effect, where, if they know that they're receiving a placebo, that can make them feel, because, it's just the psychological effect of taking medication means that you're going to improve. And so it's just that psychological impact can, show signs of improvement without the actual treatment on them. Sometimes double blinding even helps, because it occurs at two levels. The subject, the participant, doesn't know what they're receiving, whether it's a treatment or a placebo. Even the experimenter doesn't know, the researcher doesn't know whether he's administering the treatment or the placebo, because of a coding system. That makes it absolutely randomized, so that, even the researcher's bias is eliminated here. And the randomization becomes completely perfect, in the sense that the process is completely random selection, and the two groups are similar in every way, so that you can create groups that are similar in every way. So that's a touted method. Now, talking about simple random sample, okay? So by definition, what this means is it's a sample of n subjects. Give it some more. Okay. Is selected. Okay, n subjects, so n participants selected, in such a way that, this is the key part, every possible sample of the same size n has the same chance of being chosen. If you read it carefully, you can actually see what this means. Okay. So let's say we have a class of 50 students, okay, 50, and you want to create groups of 5. Okay, so there will be 10 groups, you would think, right? But what we're doing here is, if these groups are distinct, groups of 10, meaning a person is not in two groups, okay? So they're independent groups, well, you have 10 groups, 5 each, okay? And that's one thing. Or you could create groups of 5, right, where it's just a sample group of 5. So your participants can be in multiple groups of 5, okay? But you can't have that same person repeating the same group. That is meaningless, right? How can same person be repeated twice? So you understand what I mean by independent groups of 5 where the participant is not present in any other group. They're all distinct groups versus uh, um, dividing this class into all possible groups of 5. And that is what is explained here. Not independent groups of 5, but all possible groups of 5. So, the student can be in the first group of 5, in the 7th group of 5, in the 50th group of 5. So you can have so many groups of 5. And when you choose one particular group of 5, there you have an equal chance. Any group has the same chance of being chosen. Does it make sense? So that the person could be in any group, and there is a chance of selecting that person in from a group of in a group of 5, where any group of 5 had the same chance of being selected. That is keeping it simple, random sample. So now we have different kinds of sampling. Meaning, how do we divide them into groups? And, simple random sample is the way to go. Okay. So how do we divide them into groups? Sometimes they're known as random sample, not simple. But random sample is a little different because it has a weaker requirement that all members of the population have the same chance. Not all members in that same sample size has the same chance. So there's a difference there. So simple random sample is the way to go. But we have certain other types of sampling that we can use. So let's start with systematic sampling. So you have this population and you want to draw a sample from it, right, to create a sub-collection. So what we do is we say, well, select a starting point, some starting point. From that point onwards, select every kth element in it. So let's say in this case, we're talking about the cars, right? So choose some starting point. So you choose this point here, this first car here, okay? And there could be, a lot of cars traveling, but you choose one particular point and kind of freeze it there. So this is your first or the starting point. And from there, you choose to say, well, I'm going to choose every third car from here. So from the starting point, this is the third car, the sixth car, then you go with the ninth car, and so on. That's called systematic sampling, where you go after every kth element. You could choose how you want it to be. Okay, you could make it the 10th, every 10th car, or every 20th car, and so on. Convenience sampling would be easy to get data. We discussed this again before. So whatever's easy, you go to a location which is easy for you. So if you are taking a survey, you might go to your friends and then do the survey, which is again easy to get because they're your friends, but they may not represent the population that you're targeting. And so this is not desired. Sometimes it is convenient, so we just do it. That's why it's called convenience sampling. When we talk about stratified sampling, what happens here is that strata means groups, subgroups. So what you're saying is take the population and subdivide it to at least 2 different subgroups, okay, 2 strata they call it, so that the subjects within the same subgroup will share the same characteristics. Okay, so the 2 groups have the same characteristics. So you can look at this example here below. So you have 2 groups. So we took the population and divided them into 2 groups, men and women. So the men share the same characteristic that they are all male, and the women share the same characteristic that they are all female. Then we draw a sample from each group. So we randomly select 3 from the men and randomly select 3 from the women. So it's a random process, so we're not choosing the second person or the third person. So we just choose them randomly. Okay, so that is stratified sampling. So again, remember to divide it first into 2 groups, where the 2 groups within each group the subjects have the same characteristic, and then you draw a sample from each group. Then we have cluster sampling. I gave the name here, cluster. Cluster means groups or sections. So here we say divide the population area into sections, okay, into clusters, into groups. So divide the population area into sections, then randomly select some of these clusters. Okay, so randomly select some of these clusters. And third step is you will choose all the members from those selected clusters. Okay, so look at the example picture here. So this is an area where it's divided, the population area is divided into sections, like in this case, it's like between two streets, like each block. So these blocks are how the areas are divided. And then you randomly select the clusters. Okay, again, there are various software and various ways that you could randomly select these clusters. So you can number them by zones or something, put them in a hat and just randomly select them. So that is random selection. And then you can see that it's covered in red fully. That means all the members of those three selected clusters are chosen to be part of the data sample data. So that is the cluster sampling. So with that, we kind of conclude on the sampling methods. However, to make it even more robust, we have multi-stage sampling where you could have a combination of these sampling methods to create a new sampling method. So meaning in this cluster sampling, or rather actually, if you go back to this one, stratified sampling, you draw a sample from each subgroup, right? At that point, what we could do is we could then do systematic sampling, wherein you're incorporating systematic inside stratified, where you're saying, okay, I'm going to select every fourth member in the population, in the groups. So the fourth male here and the fourth female there, like that every fourth person. So 4th, 8th, 12th, 16th, and so on, right? So we could do all those combinations in these kind of sampling methods, okay? So I hope you enjoyed chapter 1. Chapter 1 was fun because we were trying to see how data appear, how to prepare data, how to analyze, how to collect data, first of all, and so on. So it's been fun. There was really no math here. It was a lot of explanation and definitions and learning this terminology. But we will get into the math part of it where we'll be using your calculator to compute these ones, okay? So I will see you in chapter 2, and thank you very much.